Okay, stuff. You have stuff for me. Well, wherever you are, please. So, um, I remember in chapter 4, we talked about multiple differential equations in multiple variables. So I had some thing as a number of operators in differentials, right? So I have some polynomial of d times x1 and some polynomial of d times x2 all the way up to some polynomial in d times xn, and that's equal to, I don't know, b1 of t. But we had more than one equation like this, so maybe I have n equations. Right? Because we were doing 2 equations in 2 variables and 3 equations in 3 variables. And the p's here is a polynomial in the d, which is our differential operator. And our xi, x1, is really x1 of t, and x2 and all the rest. And let's just say xi is xi of t. We had second derivatives and third derivatives and as many derivatives as we needed to do all of this. I want to change the ground rules a little. I want to stick with just first derivatives. And if I do that, I'd like to be able to rewrite them so that I can write dx1 dt all alone as some function of t and x1 and x2 all the way up to xn. And I'd like to be able to do that for all my derivatives. So I'm hoping that when I do this, I get something nice. Now I'm going to ask the same question I asked back in chapter 1. What the hell do you mean by nice? Well, nice in this case, ideally, would mean that these functions are linear. Okay, wait a minute. What the hell does a linear setup look like? Well, if it's linear, I want it to be linear in the x's. This is the same question I asked in chapter 1. What does it mean to be linear in the x's? Coupled pendulums. See the wobble at the beginning? And eventually it starts to smooth out. After a couple of what does it mean to be linear? Come on, people, you answered this question on the first exam. How do you know if a differential equation is linear? Yeah, that's this function gi. I want to know if that function is linear. What does that mean in terms of the xi's? What did it mean for any of our differential equations to be linear? Right. Aha. So the x's can't be multiplied by each other. They can't be like inside sines or cosines or e's or things like that. But the t's could be. It's possible for the t part to do that, which means this equation, dx1 dt, should look like something in t times x1 and something in t times x2, all the way up to something in t times xn. Now you'll notice I put double subscripts on those because this is true for not just G1, it's true for G2 and G3 and all the way up to Gn. So I could have a function of t here and here and here. And I could have a function of t for all of these. All right, wait just a second. That looks awfully familiar, except for the fact that there are derivatives on one side. That looks like a blessed matrix. Now, hang on a second. I realized I forgot something. It's not a huge something, but on each of those equations, you'll notice at the very end of the equation, there's no function of just t. I've written them all like they're homogeneous. It could be not homogeneous. So there could be, right on the end of this, f1 of t. And on the end of this, there could be fn of t. But if all of those are zero, if the f's are all zero, if fi of t is zero for all I, homogeneous system, then I can do this like a matrix. As a matter of fact, I can do this like a matrix, even if it's not. Okay, hang on a second. The hell do you mean I can do a matrix? Let's consider x1 through xn as variables. I'm going to write a giant X vector. Now, normally, I would put a vector symbol over this. The textbook just uses boldface. I'm making this a capital X. That's why it's got feet on the letters. But we can think of it as boldface. And I'm going to think of this as a vector whose functions are the entries. Well, then the derivative of this vector, capital X prime, is full of derivatives. Those f's that I were looking at the end of my functions, I can think of those as a vector full of functions as well. Capital F And here's the ugly part. I can create a matrix of all of those A's. Well, that turns that giant set of equations we were just looking at into a single equation. It's an equation in as many variables as I want, but it's a matrix equation, which is what we did in linear algebra for hours and hours and hours. The entire semester was spent on matrices. Once we got past doing row reduction operations, we actually kept dealing with the matrices themselves, right? So, by the way, if my system is homogeneous, this F is gone. Now, you all are looking at me like I just, slapped you in the face with a fish. What the is he talking about? Well, let's go back to a problem we were doing on Monday. Or something similar to that. Here. Here's a linear differential equation. And I've decided to make this one really nice. This one is oh so nice because all of the A functions are constants. Let's convert this to matrix setup. If I rewrite this as matrix setup, I'm going to let X be the vector x1, x2. Well, then this left-hand side is x prime. What's the matrix A? And F is 0 because there's no terms that are just T to go here on the end. This is homogeneous. I don't have to use X and Y, X1 and X2. I could use X and Y. Here's another example. Now, I will say this is the way this problem was presented to me in the book, but that annoys me. What's the problem here? Not a huge problem, but it is a problem. Fortunately for us, no. These things on the end can both be thought of as functions of t. 2 is a constant, but that's okay. Now, what bothers me is actually on the other side. What bothers me on the other side is the 2 and the 4. Because in my previous example, I just had x prime alone. I had y prime alone. And as a matter of fact, in the setup for all of this, I wrote dx dt all alone every time. So I just need to divide by 2 and divide by 4 before I convert this to a matrix. So really, I'm going to rewrite these equations. X prime equals 5 halves x minus 7y plus 9 halves t, and y prime equals negative 1/4 x plus 3 over 2y minus a half. Now this time, in order to take care of that 9 halves t and the 1/2 on the right-hand side, all I have to do when I create the matrix version of this is I have to use that non-homogeneous term. X prime equals matrix A times X plus this extra vector. And this extra vector contains all the things that aren't X and Y. So the 5 halves and the minus 7 and the minus 1/4 and the 3 halves go here, but here I get 9 halves t and negative 1/2. And those are my non-homogeneous bits. Maybe? Okay. This is still all set up. I haven't done about solving these things yet. But I'm just trying to figure out how I can turn this stuff from one format to another. I can go the other way as well. I could start with something that looks like it's in matrices and finish with a set of differential equations. Something like this, which is just nasty as all. Except this really isn't as bad as you might think it is. In order to get a set of equations out of this, I'm going to multiply the matrix times the vector here. Okay, linear algebra recollection. How the hell do I multiply a matrix times a vector? I turn what and multiply? Aha. So as I go across this, I go down this, right? So I think about go across the row against the column. Like I take the column, I turn it, and I multiply the first things and the second things and the third things. Just like we did when we multiplied vectors using the dot product. Calc 3, physics. You've done this before. It's just been a long time. The way I remember it is, what kind of a religious affiliated institution is Seton Hill? Yeah, well, what kind of place is this? Yes, definitely this is a strange place. But I'm not sure strange is a religion. It may be a format, but it's not a religion. This is a Roman Catholic school, right? A Catholic liberal arts school. Roman Catholic. Row, column. It's stupid, isn't it? I go across the row and down the column. I'm Roman Catholic at Seton Hill. It's a horrible way of remembering it, but I've been here 23 years, damn it, it's stuck. Okay, so wait a minute. That means that the first equation takes the first row against this column, and I get x minus y plus 2z. Now I got to deal with those other bits. So I multiply this, and I add 1 e to the minus t. And I multiply this and I get minus 3t. And that's the first row, so that goes with the first thing. Second row, second thing. Y prime is 3x minus 4y plus 1z plus 2 e to the negative t. Minus a negative 1 becomes plus 1t. Give me z prime. Yay. Now, I personally think dealing with the matrix version of this is nicer than dealing with the non-matrix version of this, but that's because I like matrices. But there's more to it than that. I only have first derivatives. Throughout this entire setup, there's only a first derivative. That makes my life a little easier. What if I had higher derivatives? You know how to solve this. Well, you know the procedure for solving this, right? We'd write the corresponding homogeneous equation. We'd write the auxiliary equation. We'd try and factor it. No, that's nasty. But there's a way to turn this equation into something that only deals with first derivatives. What do you mean? It's got a third derivative in it. I don't need it. I want to rewrite this with the third derivative all alone. What's the other side? Oh, that's already on the other side. So it's plus. Now, I'm going to replace these things, these derivatives, with more variables. So I'm going to think of y as my first variable. So I'm going to say, oh, I'm going to let y, we're just going to call that x1. Then the derivative of y, well, that would be x1 prime, wouldn't it? Let's call that a new variable, x2. Then I have y double prime. We'll call that x3. Now here's the fun part. Y triple prime is just x3 prime. Don't give it a new variable. We're only giving new variables to the stuff over here on the right. We're not giving a new variable to the thing on the left. Now, you should be asking me, why the hell did I do this? Because what I really have is 1, 2, three equations in 3 variables. And the only derivative I've got in there is a first derivative. I converted what was a third order differential equation into several first order differential equations. That's actually nicer because I only have to deal with first derivatives. Question. This is weird, Dr. Sassman. Why are you doing this garbage? Just like I talked about in chapter 4, the theory of higher order equations, and I said it was the same stuff we'd done. I'm going to make that claim here. The theory of systems of equations is really, if I can solve the small matrix cases, I can solve them all. But when I get an answer out here, I get a vector. I don't get a single function. I get x1, x2, x3. I get several functions. In the previous example, I got x and y and z. In the stuff we were doing, we got x of t and y of t. You just gave me homework on that. I got x of t and y of t and z of t. That big problem with all the graphs and the three populations that we looked at yesterday. So I'm going to get multiple functions when I solve a system of equations in matrix format. I get a solution vector. And that solution vector is a vector whose bits are functions. That's our x vector. I beg your pardon? Oh, that's the vector x1 of t, x2 of t, all the way down to xn of t. At which point my brain just lurched and said, I'm having the weirdest case of deja vu. I've seen this crap before. Where have I seen a vector made up of functions? For most of you, I expect the answer is with Dr. McNabb. Although at least you saw it with me, Jack. Calc 3. Remember r of t, our vector function? This described a path in space, right? This was a helix. This particular graph was a helix. It's a circle that keeps going up. I'm going to describe a set of functions. They're going to describe a path in however many dimensions I've got. So I can think of this set of functions the way we thought of curves in space. I also did this in 2 dimensions, right? We did r of t equals, I don't know, e to the t comma e to the negative t. I remember one of the homework problems had something that looked like that. That's what I get for teaching the same damn course for so many years. I remember some of it. But I can think of these as pictures in 2 dimensions and 3 dimensions. I'm in N. I don't know how to see in N dimensions. I don't smoke enough hallucinogenic drugs to do that. So I'm not going to try and draw these pictures in 4 and 5 and 17 dimensions. I'm just going to say, oh, there is some sort of map of what this looks like. In 2 and 3 dimensions, I will often draw these. And when we draw a graph like this, we call this something that we are creating a trajectory in a phase plane. So my curve in 2 dimensions or 3 dimensions is a trajectory in a phase plane. Sometimes in 3 dimensions, we call it a phase space. If I'm in 3D, because then it's like drawing a 3D picture. But really, this is an Etch-a-Sketch. The way that you control the horizontal, that's x of t. The way you control the vertical is y of t. Well, if I'm in 3 dimensions, then I've got a z of t. I should have three knobs, and I should be able to draw a solid object in 3 dimensions, right? That's how a 3D printer works, people. It traces out dots in 3D, controlling the X and the Y and the Z. And I draw a picture. So every time you print something in a 3D printer, I believe next week there is a brainstorming session on equitability in design, and there's a session on design to make a difference on 3D printing and adaptive behavior. So if you're interested in designing tools for adaptive behavior, there's this thing going on next Tuesday at 11 o'clock in Sicilia. I'll forward you the email if you're interested. Okay. So what the fuck? Well, something like this, or even an easier looking function. Here, let's go back to that E of t thing. Let's think about a vector. If you don't like writing it like this, you could write it as minus e to the 3t over 2 and then 2e to the 3t over 2. But I factored out the e to the 3t over 2. It's your call. You can do it either way. I think this is a solution to a given system of differential equations. Now, wait a minute. I've given you a function, in this case, a vector of functions, a solution vector, and I want you to see if it solves a differential equation. How do we check to see if a thing solves a differential equation? Chapter 1, section 2. Chapter 3 as well. We did this a bunch. How do I know that this is a solution? Plug it in and check. So I need you to take the derivative of this thing. What is x prime? That's a new vector. What do I get for my new vector? Give me some derivatives. Now, that's the left side. Let's check the right side. Okay, rows and columns. I take these two and multiply them together. What do I get? Just these two pieces. First row, first column. And then I multiply these two together and I add. What do I get here? Oh, no wonder I have a problem. Wheat. I screwed up. Because that's not going to work, is it? What do I get when I add those together? I get 3/2. What should I be getting? I should be getting a -3/2. Yeah, hang on a second. Here, please notice the copy error I made. I wrote down the problem wrong. And if you write down the problem wrong, you get the problem wrong. So let me go back and fix that. There should be a negative here, and that means there should be a negative here and a negative here. What does that do here to my derivatives? And should be negative. Hey, that matches. But you notice I have to go put the minus signs in on all of the powers so that it actually does match. If I make a copy error, people, I'm going to F it up. So let's fix it. Now, I do the same thing here on the bottom. And I get negative e to the negative 3t over 2. And then I get minus 2 more of them. And that gives me negative 3 e to the negative 3t over 2. And this matches. This looks exactly like what we did in chapter 4, section 1. Only we're doing it in matrices instead of just doing it with numbers or functions of t. This is the same crap I did in chapter 4. I know how to do this. I just have to remember how to do the linear algebra that goes with it. Right now, that's just matrix multiplication. There's more coming. Now, please remember back in chapter 4, we said that if we have a solution, it has an interval. Where are these functions defined? Are x1 of t and x2 of t. Where are they defined? Say again? Heard somebody mumble. Everywhere. That means my interval goes from minus infinity to infinity. If I pick a point in that interval and give you values, we could have initial values, couldn't we? I could actually do this with initial values as well. We often write that as a vector x0, and sometimes we'll just give it numbers like gamma 1, gamma 2, all the way down to gamma n. I've used all sorts of letters so far. I didn't want to give you another x, y, z, t, whatever. So they stuck Greek ones in here. Fine. Stupid book with their crazy alphabets. But that means, where these are all constants, means I have an initial value problem. And the initial value problem looks like x prime equals ax plus f, and x of t0 is x sub 0. That's what an initial value problem looks like for systems. Okay, all the way back to chapter 4, section 1. I said if these functions are continuous, we have a solution. Well, guess what? The same thing is true here. If I have continuous functions, they all have to be continuous on some common interval, then I am guaranteed a unique solution. If I'm dealing with homogeneous equations, then I might have one or more solutions, right? I could have several different solutions that work. That means I'll get C1 times the first solution and C2 times the second solution. This is exactly the same superposition principle we used. And we'll have linear independence, like we did for our Wronskian. I'll be able to do that in all of these. If I can find independent solutions, then I have a fundamental set of solutions. These are even the same damn terms we used in chapter 4. If I have a non-homogeneous system, I'm going to have to find a particular solution, which means when I go to solve these things, I'm going to end up with something that looks like I'm going to get C1 times some vector times a function of t. I'm going to get C2 times some vector times a function of t. All the way up to Cn times some vector. These are going to be the parts that come from the homogeneous part. That's our corresponding homogeneous solution. And then I'm going to get the particular solution for my non-homogeneous part. And it's also going to be a vector made up of functions. Which means I'm going to have to use the same tricks we used before. And I'm going to have to say, oh, I'm going to need to do undetermined coefficients. I'm going to need to do variation of parameters or something like that. Page 352. Here's what our general solution looks like. Number times vector, number times vector, number times vector. All those XC bits, those are from the homogeneous one. And then there's some particular solution. Down here, example 9 gives us a particular setup. Please notice, we're given a solution vector with e to the negative 2t in it. We're given another solution vector with e to 6t in it. And then we're given a particular solution. So C1 times the first vector times the function, C2 times the second vector times the function, and then my particular solution. Now, $64,000 question. Where did these come from? And the answer is a trick you already know from linear algebra. I want you to get eigenvalues. But that is something we will continue looking at on Friday. Cody, you're going to need to camp with me for a while. It's the office linear algebra. I will see you all then. Have a wonderful rest of your day. If you came in late, I need your homework.